Hello there. Welcome to the Science Owl Station channel. Today we begin a gentle journey beneath the vast ceiling of the night sky, where tiny sparks of light drift across the darkness like quiet whispers from the universe. Imagine, for a moment, that you are standing far away from the glow of cities, somewhere calm and open. The air is cool. The sky above you stretches endlessly, deep and velvety, scattered with patient stars. And then, without warning, a thin line of light slides across that darkness. Swift, silent, and fleeting. A meteor. Perhaps you have seen one before. Perhaps you have waited patiently, eyes fixed upward, hoping for that brief and magical streak. It happens so quickly that many people miss it entirely. But when you do catch it, even for a second, something in the mind becomes still. The universe suddenly feels closer. Tonight, we are exploring one of the most beautiful and quietly mysterious phenomena visible from Earth: meteor showers. Before we continue, I'd love to know where you are listening from tonight. Perhaps you're in a quiet room somewhere in the world. Perhaps it is late evening, or perhaps the early hours before dawn. Leave a comment telling us your location and the time where you are. It's always comforting to imagine this small community of night listeners scattered across the planet, all drifting through these cosmic stories together. And if you enjoy slow, calming explorations of science and the universe, consider subscribing and leaving a like. It helps the channel grow and allows more curious minds to discover these peaceful journeys through knowledge. Now, let's return to the sky. Meteor showers are often described in simple terms. Many shooting stars appearing across the night sky. But what makes them special is not just the number of meteors we see. It is the way they appear to emerge from a single point in the heavens. During an ordinary night, you might see one meteor here or there, a solitary streak cutting briefly across the stars. But during a meteor shower, dozens, sometimes hundreds of these streaks can appear within a single hour. They arrive like a gentle rain of light, falling silently through the darkness. And strangely, when observers watch carefully, these meteors seem to come from the same region of the sky, as if they are radiating outward from an invisible source. This point is not a star. It is not an explosion, and it is not a portal in the heavens. It is simply an illusion created by perspective, a trick of geometry and motion quietly unfolding above us. To understand this, imagine standing on a long straight road. If you look far into the distance, the road appears to narrow until both sides meet at a single point on the horizon. In reality, of course, the road remains parallel the entire way. But our eyes see those parallel lines converging into one distant point. Meteor showers behave in a very similar way. In space, countless tiny particles move along nearly parallel paths, traveling together in the same direction. But from our viewpoint on Earth, these parallel paths appear to spread outward from a single location in the sky, the radiant. So when a meteor shower occurs, what we are really seeing is Earth quietly drifting through a stream of cosmic debris, while those tiny particles rush into our atmosphere and burn briefly as streaks of light. But from our perspective below, the sky becomes a stage where these lines of light seem to burst outward like sparks from a celestial firework. It is a remarkably gentle spectacle. There is no sound, no explosion, only silent motion across the stars. And yet the human mind has been fascinated by this phenomenon for thousands of years. Long before telescopes existed, People watched the sky with deep curiosity. They saw these sudden flashes and wondered what they meant. In many ancient cultures, meteors were interpreted as messages from the heavens. Some believed they were omens. Others thought they were spirits traveling across the sky. In medieval Europe, a meteor streaking overhead might be taken as a sign of change or warning. In ancient China, astronomers carefully recorded the appearance of falling stars in detailed sky chronicles that still exist today. But the true nature of meteor showers remained a mystery for most of human history. Even as late as the early 1800s, scientists still debated their origin. Some thought meteors were atmospheric phenomena, perhaps electrical discharges high in the sky. Others suggested volcanic gases igniting in the upper air. It wasn't until a remarkable event in 1833 that scientists began to understand what was really happening. On a cold November morning that year, observers across North America witnessed one of the most extraordinary meteor storms ever recorded. Thousands upon thousands of meteors filled the sky. Some estimates suggested that hundreds of meteors appeared every minute. The sky looked as if it were raining stars. People woke in the early hours believing the end of the world had arrived. Churches filled with frightened crowds praying through the night. But for astronomers, that event revealed an important clue. All the meteors seemed to originate from the same area of the sky, the constellation Leo. This discovery suggested that meteor showers were not random atmospheric flashes. They were celestial events connected to something much larger moving through space. And slowly, piece by piece, scientists began to realize that these brilliant streaks were caused by tiny fragments of cosmic material entering Earth's atmosphere at tremendous speed. Not stars falling, but dust. Tiny grains of rock and metal, no larger than sand, traveling silently through the solar system until their path intersected with Earth. When those grains strike the upper atmosphere, they encounter air molecules rushing toward them at extraordinary speeds. The resulting compression and heat cause the surrounding air to glow, producing the luminous streak we call a meteor. A brief flash, a fleeting trace of light, often lasting no more than a second or two. And yet those tiny sparks reveal something extraordinary about our planet. Earth is not isolated in space. It is constantly moving through a dynamic environment filled with particles, debris, and remnants from ancient cosmic journeys. Meteor showers are simply the moments when our planet passes through one of these invisible rivers of dust. And when that happens, the sky above us becomes a quiet theater of falling light. So tonight, as we begin this exploration, imagine yourself lying back under an open sky. The stars are steady and distant. The night air is still. And somewhere high above, far beyond the clouds, Earth continues its silent journey through the solar system, occasionally brushing through a delicate trail of ancient cosmic dust. Each tiny grain waits patiently in darkness, until, for a brief moment, it touches the atmosphere of our world and becomes a shooting star. If we remain still beneath the night sky long enough, something subtle begins to reveal itself. The stars appear motionless, almost eternal, yet our planet is quietly moving through space at extraordinary speed. Every second, Earth travels nearly 30 kilometers along its orbit around the Sun. It is a journey so smooth and constant that we rarely notice it. But sometimes, along that enormous path, our planet encounters something unexpected. Not planets, not moons, not massive objects drifting through the solar system. Instead, we meet delicate streams of cosmic dust, ancient trails of debris scattered across space like invisible rivers. And when Earth passes through one of these dusty pathways, the quiet spectacle we call a meteor shower begins. To understand this better, imagine the solar system not as empty space, but as a vast environment filled with subtle remnants of past journeys. Long ago, certain celestial visitors, especially comets, traveled close to the sun. As they did, heat from the sun loosened small fragments from their icy surfaces. Tiny grains of rock and dust escaped into space and slowly spread out along the comet's orbital path. Over centuries, sometimes thousands of years, these particles form long streams that follow the same route around the sun as the comet itself. They drift silently, moving through darkness, invisible to human eyes. But eventually, Earth crosses one of these streams, and that is when the sky begins to glow with falling light. When our planet enters one of these particle streams, the tiny fragments collide with Earth's atmosphere at incredible speeds. From the ground, we see them as streaks of light flashing across the sky. But what we are really witnessing is something far larger. Earth sailing through a cloud of ancient cosmic dust. These particles have often traveled for thousands of years before meeting our atmosphere. Some may have been drifting since before human civilizations existed. They circle the sun patiently, following the gravitational paths laid out long ago by comets and asteroids. When Earth intersects that path, even briefly, the result can be a meteor shower. Sometimes the encounter lasts only a few hours. Other times it stretches across several nights. The sky becomes active, as if the universe itself were quietly sprinkling sparks across the darkness. And yet, the particles responsible are astonishingly small. Many of them are no larger than grains of sand. It may seem surprising that something so tiny can produce such a bright streak in the sky. But speed changes everything. When these particles collide with the upper atmosphere, they do so at speeds often exceeding 20, 30, or even 70 kilometers per second. At such velocities, even the smallest fragment carries tremendous energy. The air in front of the particle compresses violently, heating to thousands of degrees. That heat excites atoms in the atmosphere, causing them to emit light. For a moment, a glowing trail forms, a thin thread of brightness slicing through the night, and then it fades. The entire event often lasts less than a heartbeat. Yet during a meteor shower, many such particles arrive in quick succession, creating a delicate rain of light. The reason we see so many meteors during these events is because Earth is not just encountering a single particle at a time. Instead, it is moving through an entire stream of debris left behind by an ancient traveler of the solar system. Those streams can stretch millions of kilometers through space. Imagine a long ribbon of dust orbiting the sun, thin but vast, like a cosmic pathway drawn across the darkness. When Earth crosses that ribbon, we experience a meteor shower. But there is another fascinating detail hidden within this phenomenon. The particles in a meteor stream are not randomly scattered in all directions. They tend to move in nearly parallel paths, following the same orbit that created them. This means they approach Earth from roughly the same direction in space. As our planet moves forward along its orbit, it effectively runs into these particles head-on, much like a car driving through falling snow. If you have ever watched snowflakes strike a windshield while traveling down a road, you might remember how they appear to come from a single direction ahead of the car. Even though the snow is falling gently everywhere, the motion of the vehicle makes it seem as though all the flakes are rushing toward one point. Earth's motion through space creates a similar illusion. From the ground, meteors appear to radiate outward from a single location in the sky, called the radiant. But in reality, the particles are moving along parallel paths. It is simply our perspective, combined with Earth's forward motion, that makes the meteors seem to burst outward like sparks from a distant point among the stars. The radiant itself is not a physical object. It is just the place in the sky where the meteor paths appear to converge. During a meteor shower, if you watch long enough, you will notice streaks appearing in many directions across the sky. But if you trace those streaks backward, they all point toward the same region. This simple geometric illusion helps astronomers identify which meteor shower is taking place. Because each stream of debris follows a different orbit around the sun, each one intersects Earth from a slightly different direction. As a result, each meteor shower has its own radiant located in a specific constellation. Over time, these repeating celestial encounters became predictable. Astronomers learned that certain meteor showers return every year at roughly the same time. This happens because Earth follows the same orbital path each year, crossing the same dust streams again and again. The solar system, despite its vastness, contains these quiet patterns, rhythms of motion that repeat across centuries. Each year, as our planet reaches the same point in its orbit, it brushes once more against the invisible trails left behind by ancient comets. And once again, the sky lights up with falling stars. If you could step far outside the solar system and look back from a great distance, you might see something remarkable. You would see Earth moving along its orbit like a traveler following a circular path around the sun. And along that path, there would be faint bands of dust scattered across certain regions, remnants of cosmic visitors long gone. Whenever Earth crosses one of those bands, the atmosphere briefly sparkles. Tiny particles that drifted silently for centuries suddenly blaze into light for just a second. Then they vanish. The dust stream continues on its orbit, waiting patiently for the next encounter with our world. And Earth continues its steady journey through space, sometimes alone in the darkness, and sometimes passing gently through a hidden river of stardust. As our quiet journey through the night sky continues, we begin to notice that meteor showers are not random events. They do not simply appear without cause, nor do they arrive from empty space without origin. Each meteor shower has a history, a story that often begins with one of the most mysterious travelers in the solar system, the comet. For centuries, comets have fascinated and unsettled human observers. Ancient sky watchers saw them as wandering stars with glowing tails, drifting slowly across the heavens. Unlike the steady stars and predictable planets, comets appeared suddenly and unpredictably, sometimes remaining visible for weeks before fading again into the darkness of space. To early civilizations, they were signs of change, omens written across the sky. But today we understand them differently. A comet is essentially a small, icy body composed of frozen gases, dust, and rock, sometimes described poetically as a dirty snowball. Most comets originate far from the sun, in distant regions of the solar system where temperatures are extremely cold. In these remote places, water ice, carbon dioxide, methane, and other frozen materials remain solid for millions or even billions of years. But occasionally, gravitational interactions send a comet drifting inward toward the sun. And when that happens, something remarkable begins. As the comet approaches the inner solar system, sunlight grows stronger and warmer. The heat begins to transform the frozen materials on the comet's surface directly into gas through a process called sublimation. Instead of melting into liquid first, the ice turns straight into vapor. Jets of gas erupt from the comet's surface. These outbursts carry tiny particles of dust and rock away from the comet, releasing them gently into space. Over time, this continuous shedding of material creates a long trail of debris following the comet along its orbit. The bright tail we often see extending behind a comet is made partly of gas and partly of dust illuminated by sunlight. But the dust does not simply disappear. Much of it continues to orbit the sun along the same path as the comet that released it. Slowly, over many journeys around the sun, this dust spreads out into a long stream, a thin ribbon of particles stretching across millions of kilometers of space. This ribbon becomes the source of a meteor shower. One of the most famous examples of this process involves a comet called Swift-Tuttle. Comet Swift-Tuttle was first discovered in 1862 by two astronomers, Lewis Swift and Horace Tuttle. At the time, it appeared as a faint glowing object moving slowly against the background of stars. Like many comets, it followed a long and elongated orbit around the sun. Swift-Tuttle takes about 133 years to complete a single trip around the sun. That means that during most human lifetimes, the comet itself is far away, invisible in the outer reaches of the solar system. But the dust it leaves behind remains. Over thousands of years, Swift-Tuttle has scattered countless tiny particles along its orbital path. That stream of debris continues to circle the sun even when the comet itself is distant. Every year in mid-August, Earth passes directly through part of that dusty trail. When it does, the particles enter our atmosphere and ignite briefly into glowing streaks of light. This annual event is known as the Perseid meteor shower. For many observers, the Perseids are the most beloved meteor shower of the year. Warm summer nights make it comfortable to lie beneath the sky and watch patiently as meteors glide overhead. The Perseids are famous not only for their beauty, but also for their reliability. Year after year, they return with impressive activity, sometimes producing dozens of meteors each hour during their peak. And each one of those meteors is a tiny fragment once released by Swift-Tuttle. In other words, when we watch the Perseids, we are witnessing pieces of an ancient comet burning high above our planet. It is a quiet reminder that the solar system is not static. Objects travel vast distances, leaving subtle traces of their journeys behind them. Comets act almost like gardeners of the cosmos, scattering seeds of dust along their paths. Those seeds remain suspended in space until a planet like Earth happens to pass through them. Then, for a brief moment, the sky blossoms with light. Not all meteor showers originate from comets, however. In some cases, the source can be an asteroid, a rocky body rather than an icy one. While asteroids usually remain intact, collisions or thermal stresses can sometimes release fragments into space. One particularly interesting example involves an object known as 3200 Phaeton. Unlike typical comets, Phaeton appears mostly rocky and does not display the dramatic icy tail we associate with comet activity. Yet it still produces a large stream of debris that Earth encounters every December, creating the Geminid meteor shower. Astronomers believe that Phaeton may be a kind of hybrid object, something between a comet and an asteroid, slowly shedding fragments due to intense heating during its close passes to the Sun. But whether the source is a comet or an asteroid, the result can be the same. A long, invisible trail of particles forms along the object's orbit, and eventually Earth crosses that path. The remarkable thing is how ancient many of these dust streams are. Some were created thousands of years ago, long before recorded history. Others may be much older still. The particles themselves drift quietly through space, almost unchanged, waiting patiently along their orbital path. Most of the time, nothing happens. But when Earth arrives at the right place in its orbit, the encounter becomes visible. Suddenly, the sky begins to sparkle. What we see as a meteor shower is really the intersection of two journeys: Earth's steady path around the Sun and the ancient orbit of a comet that passed by long ago. For a few nights each year, those two paths cross. And when they do, fragments of an icy traveler from deep space briefly transform into streaks of fire across our atmosphere. Tiny grains of dust, ancient remnants of a wandering comet, burning softly above our sleeping world. As we continue drifting gently through this quiet exploration of the night sky, it becomes clear that the bright streaks we call meteors begin their story long before they ever reach Earth. Long before they glow across the sky for a fleeting second, these particles exist in deep space as something much more modest and unremarkable. They are called meteoroids. A meteoroid is simply a small fragment of rock or metal traveling through space. Some originate from comets, others from asteroids, and a few may even be fragments blasted from the surfaces of planets or moons during ancient impacts. But regardless of their origin, most meteoroids are incredibly small. Many are no larger than a grain of sand. Some are the size of tiny pebbles. Only a few reach the size of a marble or a small stone. Yet despite their modest size, these particles travel through the solar system with astonishing speed, quietly circling the Sun along paths shaped by gravity. In the darkness of space, they drift silently, invisible to human eyes. There is no glow around them, no fiery tail. They are simply small pieces of cosmic debris moving through the vast emptiness between planets. If you could somehow float nearby one of these meteoroids in space, it would appear dull and lifeless, perhaps a tiny speck of rock tumbling slowly through sunlight. Nothing about it would suggest the brief brilliance it might someday produce. And yet, its journey is already underway. Many meteoroids begin their existence as fragments released from comets. When a comet approaches the Sun and begins shedding dust, those particles spread along its orbit. Some remain clustered together, while others slowly drift farther apart over centuries. Gravity from planets, especially giant Jupiter, can gently alter their paths. Solar radiation can nudge them ever so slightly. Collisions with other particles may break them into smaller pieces. Over long periods of time, these processes create vast clouds of microscopic debris scattered across the solar system. Yet, despite the enormous distances involved, many of these particles continue to follow predictable orbital patterns. Some of them travel along paths that intersect Earth's orbit. When that happens, their quiet journey through space enters its final stage. But before we reach that dramatic moment, It is worth pausing to imagine how these tiny fragments spend most of their existence. For perhaps thousands of years, a meteoroid may circle the sun again and again without encountering anything at all. One orbit may take several years. Another may take decades or centuries depending on its distance from the sun. Each time it travels its path, it drifts through the same regions of space, passing the same planets, following the same invisible gravitational highways. But the solar system is enormous. Even though countless particles exist within it, the distances between them are vast. Most meteoroids never collide with planets or other objects. They simply continue their silent revolutions around the sun. Sometimes their orbit crosses that of Earth, but timing is everything. If Earth has already passed that point, the meteoroid continues onward unhindered. But eventually, one day, the timing aligns. Earth arrives at exactly the right place along its orbit at the exact moment a meteoroid passes through. Two paths intersect, and suddenly the tiny particle finds itself approaching a world. From the perspective of the meteoroid, the encounter happens incredibly fast. Earth's gravitational pull begins to influence its trajectory, drawing it inward. The particle accelerates as it approaches the planet, moving faster and faster relative to the atmosphere below. At first, nothing seems different. Space around the particle remains dark and empty. But then, gradually, the uppermost fringes of Earth's atmosphere appear. An extremely thin layer of gas extending hundreds of kilometers above the surface. Even at those great heights, the atmosphere is not completely empty. Molecules of oxygen and nitrogen float in extremely low densities. To us on the ground, that region would still feel like the vacuum of space. But to a meteoroid racing toward Earth at tens of kilometers per second, even this faint presence of gas becomes significant. At such tremendous speed, the particle begins colliding with atmospheric molecules. The interaction is violent. Air molecules slam into the meteoroid with enormous energy. The gas in front of the particle compresses rapidly, heating to extreme temperatures. Within moments, the once cold fragment of space debris is surrounded by a glowing sheath of superheated air. This is the beginning of the meteor. But interestingly, the light we see in the sky is not produced mainly by the rock itself burning like a spark. Instead, most of the glow comes from the heated gases surrounding the particle. The air becomes ionized, forming plasma, a glowing state of matter where atoms lose their electrons due to intense heat. This luminous plasma creates the bright streak that observers see from the ground. As the meteoroid continues its descent, it begins to erode. Tiny layers of material vaporize and peel away under the intense heat and pressure. This process is known as ablation. For most meteoroids, this stage lasts only a few seconds. The particle gradually disintegrates high in the atmosphere, often between 70 and 120 kilometers above Earth's surface. By the time the glow fades, the original meteoroid is usually completely gone. A tiny fragment that spent centuries drifting through space has vanished in a brief flash of light. But during meteor showers, many such particles arrive one after another. Each one follows its own path into the atmosphere, creating a delicate sequence of luminous streaks across the sky. And although each individual meteoroid is small and short-lived, together they form one of the most peaceful spectacles in the night sky, a quiet rain of cosmic dust. Tiny travelers from deep space. each one completing its long journey with a moment of light above our world. As the small meteoroid continues its silent descent toward Earth, something extraordinary begins to unfold. Only moments ago, the particle was drifting peacefully through the vacuum of space, moving along its quiet orbit around the sun. But now, as it approaches our planet, the environment around it changes rapidly. Ahead lies Earth's atmosphere, a thin but powerful shield of gases wrapped gently around the planet. From space, the atmosphere appears almost invisible, just a faint blue halo glowing at the edge of the world. Compared to the enormous size of Earth, it is astonishingly thin. If our planet were the size of a large apple, the atmosphere would be little thicker than the skin of that apple. Yet despite its delicate appearance, this thin layer of gas plays a crucial role in shaping what we see during a meteor shower. As the meteoroid approaches Earth, gravity gradually pulls it inward. The speed increases relative to the planet below. Some meteoroids already move extremely fast along their solar orbits, and when combined with Earth's own orbital motion, the encounter can occur at astonishing velocities. Many meteoroids strike the atmosphere traveling between 20 and 70 kilometers per second. To imagine such speed, consider that a passenger airplane travels around 250 meters per second. A meteoroid can move more than 100 times faster than that. At these speeds, even the thinnest traces of air become significant. The first contact between a meteoroid and the atmosphere occurs at extremely high altitudes, often around 120 kilometers above the surface of Earth. At that height, the air is still extraordinarily thin, almost like space itself. But for a particle moving tens of kilometers every second, even these few scattered molecules of gas begin to collide violently with its surface. Each collision releases energy, and those collisions happen not once, but millions of times every second. As the meteoroid plows through the upper atmosphere, air molecules pile up in front of it, unable to move aside quickly enough. This compression of air creates intense heat. Interestingly, the heating process is not caused mainly by friction in the ordinary sense. Instead, it is the compression of air that produces the extreme temperatures. When gases are compressed rapidly, their temperature rises dramatically. The air in front of the meteoroid becomes superheated, reaching temperatures of several thousand degrees Celsius. This intense heat spreads around the particle, forming a glowing envelope of hot gas. At the same time, the meteoroid itself begins to heat rapidly. The outer layers of rock or metal start to melt and vaporize. Tiny fragments break away and are carried backward along the flow of hot air. This process, known as ablation, gradually erodes the meteoroid as it travels deeper into the atmosphere. For many particles, the entire event unfolds within just a few seconds. From the ground, observers see only the result: a thin, brilliant line of light suddenly appearing across the sky. The meteor streak begins at high altitude where the atmosphere is thin. As the meteoroid descends, the glow grows brighter because the air becomes denser, producing more heat and more luminous gas. Often the meteor reaches its peak brightness somewhere between 80 and 100 kilometers above Earth's surface. At that height, the meteoroid is already disintegrating rapidly. Tiny droplets of molten material peel away from the particle, vaporizing almost instantly in the extreme heat. The glowing trail left behind is composed of ionized gases and microscopic fragments. Sometimes this trail fades immediately, but in other cases, The glowing path lingers briefly in the sky like a faint ghost of the meteor's passage. These lingering trails are called persistent trains. High-altitude winds can slowly twist and stretch them, causing delicate shapes to ripple across the darkness. For several seconds, sometimes even minutes, the faint trail remains visible, drifting gently among the stars before dissolving completely. Meanwhile, the meteoroid itself continues to lose mass rapidly. For most meteoroids, the original particle is completely consumed before it ever reaches lower altitudes. By the time the meteor fades from view, nothing remains except a small cloud of vaporized atoms scattered through the upper atmosphere. The entire journey, from the first atmospheric contact to complete disintegration, usually lasts no longer than a few seconds. Yet during meteor showers, this process repeats again and again. Each particle enters the atmosphere along a slightly different path, producing a unique streak across the sky. Some meteors appear faint and delicate, barely visible against the background of stars. Others blaze brightly, leaving vivid trails that catch the eye instantly. Occasionally, a larger fragment produces an especially brilliant meteor known as a fireball. Fireballs can outshine the brightest stars, sometimes even rivaling the brightness of the moon for a brief moment. These spectacular events occur when larger meteoroids, perhaps the size of a pebble or small stone, survive longer in the atmosphere before disintegrating. But even these larger fragments rarely reach the ground. Earth's atmosphere is remarkably effective at protecting the surface below. Most meteoroids are destroyed high above the planet, transforming into glowing streaks that vanish long before they could pose any danger. So when we watch a meteor shower from the ground, we are witnessing a natural defense system quietly at work. Tiny fragments from deep space encounter our atmosphere and release their energy high in the sky, far above cities, forests, and oceans. Each one burns briefly, illuminating the darkness with a moment of light, and then it is gone. A particle that may have drifted through the solar system for thousands of years ends its journey in a quiet flash high above our world, leaving only a fading streak across the stars. If we look carefully at the path of a meteor as it glides across the sky, we may notice that its brightness seems almost alive. The streak sometimes flickers, sometimes glows steadily, and occasionally flares for a brief moment before fading away. This gentle dance of light is not random. It is the visible result of physical processes unfolding at extreme speed high above the Earth. The glow of a meteor is created through a fascinating interaction between a tiny fragment of cosmic debris and the gases of our atmosphere. Earlier, we mentioned that a meteoroid entering the atmosphere compresses the air in front of it, heating that gas to extraordinary temperatures. That heat is powerful enough to change the state of the surrounding atoms. Under such intense energy, the atoms of oxygen and nitrogen in the atmosphere lose some of their electrons. When this happens, the atoms become electrically charged and form what scientists call plasma, a glowing mixture of ions and free electrons. Plasma behaves very differently from ordinary gas. It can conduct electricity, respond to magnetic fields, and most importantly for our story, it can emit light. As the plasma surrounding the meteoroid forms, atoms and molecules become excited by the intense heat and collisions. Their electrons jump into higher energy states. But these excited states are unstable. The electrons soon fall back to their original positions. And when they do, they release energy in the form of light. This light is what creates the luminous streak we see across the night sky. So, although we often say that the meteoroid burns up, the meteor's brightness is not exactly like a piece of wood burning in a fire. Instead, it is more like a glowing trail of energized air, briefly illuminated by the violent passage of a tiny particle moving at tremendous speed. The meteoroid itself contributes to the glow as well. As its outer layers heat and vaporize, atoms from the particle mix with the surrounding plasma. These atoms also emit light as they cool and settle back into stable states. Together, the heated atmospheric gases and the vaporized material from the meteoroid create the meteor's characteristic glow. This is why meteors can sometimes display different colors as they streak through the sky. Each chemical element emits light at specific wavelengths when excited by heat. These wavelengths correspond to different colors visible to our eyes. If sodium atoms are present, the meteor may glow with a soft yellow or orange hue. Sodium is commonly found in many types of cosmic dust and can produce warm golden tones in the meteor trail. Magnesium, another element frequently found in meteoroids, often produces a greenish light. This green glow can sometimes be quite striking, especially in brighter meteors. Iron can contribute yellow or golden colors, while calcium may create faint violet tones near the edges of the glowing trail. Meanwhile, the atmospheric gases themselves also influence the color of the meteor. Oxygen and nitrogen in the air can produce red, orange, or bluish tones depending on the temperature and energy of the plasma. The exact mixture of colors depends on many factors: the speed of the meteoroid, its chemical composition, and the density of the atmosphere at the altitude where it is glowing. Sometimes these colors blend together, producing a soft white streak. Other times observers may notice subtle shades of green, yellow, or even pale blue flickering within the meteor's path. But the colors are only part of the story. Another fascinating feature of meteors is the brief trail they leave behind. As the meteoroid tears through the atmosphere, it creates a narrow column of ionized gas along its path. This glowing column can sometimes remain visible for several seconds after the meteor itself has vanished. These lingering trails are known as persistent trains. At altitudes of around 90 to 100 kilometers, winds in the upper atmosphere begin to influence the shape of these trails. Though we cannot feel these winds on the ground, they move steadily through the thin air high above. Slowly, the faint trail begins to twist and drift. What was once a straight glowing line may gradually bend into delicate curls or spirals as the winds stretch the cloud of ionized gas. Under especially favorable conditions, these ghostly trails can remain visible for several minutes before fading completely. Watching such a trail slowly dissolve in the sky can feel almost dreamlike. The meteor itself lasted only a second, yet the memory of its passage lingers quietly above us. Sometimes observers describe these fading trails as if the sky itself had been gently brushed by light. But despite their beauty, meteors remain delicate events. Most are created by particles no larger than grains of sand. Their energy is enormous because of their speed, but their mass is extremely small. As a result, the glowing meteor is usually gone almost as soon as it appears. A brief flash, a silent line across the stars, then darkness returns. And yet, during a meteor shower, this process repeats again and again. One streak appears, then another, sometimes several within a single minute. Each one follows the same physical process. a tiny particle from space colliding with Earth's atmosphere, compressing the air, creating plasma, and releasing light. It is a remarkable transformation. A cold fragment of cosmic dust, drifting unnoticed through the solar system for centuries, suddenly becomes a bright streak of fire in our sky. Then it disappears forever. But for those watching below, that fleeting moment of light can feel timeless. A gentle reminder that even the smallest pieces of the universe can briefly illuminate the darkness. If you watch a meteor shower long enough, a curious pattern slowly begins to emerge. At first, the meteors appear scattered randomly across the sky. One streak flashes overhead, another glides across the horizon, and a third may appear far to the side. But after several minutes of quiet observation, something subtle becomes noticeable. The streaks are not entirely random. If you mentally trace each meteor's path backward across the sky, many of them seem to point toward the same distant region among the stars. It is as if the meteors are flying outward from a single invisible source. Astronomers call this point the radiant. The radiant is one of the most important features of a meteor shower, yet it is also one of the most misunderstood. It is not a physical object in space. There is no star exploding there, no portal, and no cluster of particles waiting to burst outward. Instead, the radiant is simply a matter of perspective. To understand why meteors appear to radiate from one point, imagine standing on a long straight railway track. The two rails extend far into the distance, remaining perfectly parallel. But as you look toward the horizon, the rails seem to converge until they meet at a single point. Of course, the rails never truly meet. The appearance of convergence is only a trick of perspective created by distance. Meteor showers behave in exactly the same way. The particles in a meteoroid stream travel through space along nearly parallel paths. They are moving together, following the orbit left behind by the comet or asteroid that created them. But when Earth enters this stream, the particles rush toward our atmosphere from roughly the same direction. Because they are moving almost parallel to one another, our eyes interpret their paths the same way we interpret those railway tracks. Each meteor streak appears to originate from a single distant point in the sky, the radiant. In reality, the particles are not spreading outward from that point. They are simply moving in parallel lines toward Earth. The illusion becomes especially clear during strong meteor showers. Observers can watch dozens of meteors streak across the sky, yet nearly all of their paths can be traced back toward the radiant. Interestingly, meteors that appear farther from the radiant often produce longer streaks across the sky. This happens because of geometry. When a meteor appears close to the radiant, it is moving almost directly toward the observer. As a result, its path across the sky appears short. But meteors appearing farther away from the radiant cross the atmosphere at an angle relative to the observer. This makes their streaks appear longer and more dramatic as they glide across a larger portion of the sky. For this reason, experienced meteor watchers often look slightly away from the radiant when observing a meteor shower. This allows them to see longer, more striking meteor trails. The radiant itself slowly moves across the sky during the night. Because Earth is rotating, the stars appear to rise in the east and set in the west. The radiant follows this same motion. Early in the evening, it may sit low near the horizon. As the night progresses, it climbs higher into the sky. And this change has an important effect on meteor activity. When the radiant is low, Many meteors that enter the atmosphere travel horizontally relative to the observer's location. Some may even occur below the horizon and remain invisible. But as the radiant rises higher in the sky, more meteoroids enter the atmosphere directly above the observer. This increases the number of visible meteors. That is why meteor showers are usually best observed after midnight. By that time, the radiant has climbed higher into the sky, and the observer's location on Earth is facing more directly into the incoming stream of particles. Another subtle detail makes the radiant even more interesting. Because the meteoroid stream follows a specific orbit around the Sun, the direction from which the particles approach Earth remains consistent each year. This means that the radiant of a particular meteor shower always appears in roughly the same region of the sky. For example, the Perseid meteor shower has its radiant in the constellation Perseus. Every August, when Earth crosses the Perseid dust stream, the meteors appear to radiate from that same constellation. Other meteor showers have radiants located in different constellations. The Geminids radiate from Gemini, the Leonids from Leo, the Orionids from Orion. These names help astronomers and observers identify which meteor shower is currently active. But even though the radiant appears fixed among the stars, it is actually the result of Earth's motion through space intersecting with a stream of particles traveling along their own orbit. Two cosmic paths crossing, one belonging to our planet, the other belonging to ancient debris scattered long ago by a comet or asteroid. When these paths intersect, the radiant appears. And from that quiet point in the sky, lines of light begin to spread outward across the darkness. Silent streaks tracing the invisible geometry of our motion through the solar system. Each meteor reminding us that even the emptiest parts of space contain hidden patterns waiting to reveal themselves to patient observers. Once astronomers began to understand the idea of the radiant, another question naturally followed. If different meteor showers appear to originate from different points in the sky, how do we identify and name them? The answer turns out to be surprisingly simple, and it connects meteor showers to one of the oldest traditions in astronomy: the constellations. For thousands of years, humans have divided the night sky into recognizable patterns of stars. These patterns, the constellations, served as celestial landmarks, helping early observers navigate the heavens long before modern telescopes or scientific instruments existed. When astronomers discovered that meteor showers appear to radiate from specific regions of the sky, they realized that the easiest way to identify them was by referencing the constellation where the radiant lies. And so meteor showers began receiving names based on those constellations. If the radiant appears within the constellation Perseus, the meteor shower becomes the Perseids. If the radiant lies in Gemini, the shower is called the Geminids. If it appears in Leo, we call it the Leonids. This naming system is simple, consistent, and surprisingly poetic. Each meteor shower becomes linked not only to a stream of cosmic debris, but also to a familiar region of the sky that observers can recognize. Of course, the radiant does not always sit exactly at the center of a constellation. The boundaries between constellations are somewhat arbitrary, and sometimes the radiant may lie near the edge of one pattern or very close to another. But the general location is enough for astronomers to assign a name. Once a meteor shower is identified and studied, its name becomes part of astronomical tradition. Over time, astronomers have cataloged dozens of meteor showers that occur throughout the year. Some are strong and easily visible to casual observers. Others are faint, producing only a few meteors per hour and requiring darker skies and more patient watching. But the naming system remains the same. Each shower carries the name of the constellation where its radiant appears. Interestingly, the radiant itself is not perfectly fixed. Over the course of several days, the radiant of a meteor shower slowly drifts through the sky as Earth continues moving along its orbit around the Sun. This motion is subtle but measurable. Astronomers call it radiant drift. Because Earth is moving through the meteoroid stream at a slightly different angle each night, the apparent radiant shifts gradually against the background of stars. Typically, this movement is small, perhaps a degree or so per day, but it can be detected with careful observations. Despite this slow drift, the radiant remains within the same general constellation during the meteor shower's active period. That is why the names remain stable from year to year. Another interesting detail about meteor shower names is the way they are sometimes refined or updated. As astronomers study meteor streams more closely, they may discover that the radiant lies closer to a specific star within the constellation. In such cases, the shower may be named after that star. For example, a meteor shower radiating near the star Delta Aquarii is known as the Delta Aquariids. Similarly, the Alpha Capricornids originate near the star Alpha Capricorni. This more precise naming method helps astronomers distinguish between multiple meteor showers that occur within the same constellation. Because the sky contains many overlapping meteor streams, careful naming helps avoid confusion. But for casual observers lying beneath the stars, the traditional names remain the most familiar. Perseids, Leonids, Geminids. Each name carries with it not only scientific meaning but also a sense of connection to the patterns of stars that humans have watched for millennia. These names remind us that meteor showers are not isolated events. They are part of the larger structure of the sky. When we watch a meteor streak past the constellation Perseus, we are seeing a brief spark of light against a backdrop of stars that have been guiding travelers, storytellers, and astronomers for thousands of years. And in that moment, the ancient patterns of the sky and the modern understanding of cosmic physics quietly meet. There is something calming about this connection. The meteors themselves are fleeting, lasting only seconds. But the constellations remain steady, slowly shifting across the night as Earth turns beneath them. Night after night, season after season, year after year. Every August, the Perseids return. Every December, the Geminids appear. Each meteor shower arrives at roughly the same time each year because Earth follows the same orbit around the Sun. Our planet crosses the same streams of cosmic debris again and again. And as it does, the sky briefly fills with silent streaks of light that seem to radiate from familiar star patterns. It is almost like meeting an old celestial friend. You look up, recognize the constellation, and know that the meteor shower has returned once more. A quiet cosmic rhythm repeating across generations. Each year, the same streams of dust wait patiently along Earth's orbital path. And each year, when the timing is right, the radiant rises among the stars and the gentle rain of meteors begins again. If we pause for a moment and think about the meteors that streak across the sky during a meteor shower, a curious question arises. How large are the particles that create these brilliant flashes of light? From the ground, a bright meteor can appear dramatic and powerful. Some streak across the sky like glowing arrows, leaving luminous trails that momentarily linger among the stars. It might seem natural to imagine that such displays are created by sizable rocks plunging into Earth's atmosphere. But the reality is far more delicate. Most meteors are produced by particles astonishingly small, often no larger than grains of sand. Some are even smaller than that. These tiny fragments, known as meteoroids, are usually just millimeters across. Many weigh less than a single gram. In everyday terms, they are comparable to small grains of dust you might find resting unnoticed on a windowsill. And yet, when these minuscule particles encounter Earth's atmosphere, they can produce streaks of light visible from hundreds of kilometers away. How can something so small create such a bright display? The answer, once again, lies in speed. When meteoroids enter Earth's atmosphere, they travel at extraordinary velocities, tens of kilometers per second. At such speeds, even a particle with very little mass carries a large amount of kinetic energy. As that energy is released through interactions with the atmosphere, it converts rapidly into heat and light. The meteoroid itself begins to vaporize almost instantly, while the surrounding air becomes superheated and glows brightly. So the meteor we see is not simply the rock burning. It is the atmosphere itself lighting up in response to the meteoroid's passage. Because the light comes from the heated air rather than from the rock alone, even the smallest particles can create visible meteors. This is why meteor showers often produce large numbers of faint streaks across the sky. Each one may be created by a particle no larger than a grain of sand. In fact, during strong meteor showers, Earth encounters millions of these tiny particles as it passes through the debris stream left behind by a comet or asteroid. Most of them are so small that their meteors are extremely faint, visible only from dark locations where the sky is free from artificial light. Observers in rural areas often see far more meteors than those watching from brightly lit cities. Light pollution hides the faintest streaks, leaving only the brighter meteors visible to urban observers. Occasionally, however, larger fragments appear within the debris stream. Some meteoroids may be the size of small pebbles or marbles. These slightly larger particles carry much more mass, and therefore much more energy, when they strike the atmosphere. When such fragments enter the atmosphere, they produce brighter meteors, sometimes brilliant enough to attract immediate attention even in brightly lit skies. These bright meteors are often called fireballs. Fireballs can produce intense flashes of light and may leave glowing trails that persist for several seconds or even minutes. In rare cases, very large meteoroids, perhaps the size of a fist or larger, may survive part of their descent through the atmosphere. If fragments reach the ground, they become meteorites. But such events are extremely uncommon during typical meteor showers. Most meteoroids in these showers are fragile and loosely held together. Many are composed of porous material similar to compressed dust or soft stone. When they encounter the intense heating of atmospheric entry, they disintegrate quickly and completely. Even particles the size of small pebbles often vaporize before reaching lower altitudes. This fragility is especially common among meteoroids originating from comets. Comets are composed of icy material mixed with dust and small rocky fragments. The particles they release into space are often delicate and crumbly compared to the denser rocks found in asteroids. When these fragile particles enter Earth's atmosphere, they break apart easily, creating the faint but beautiful streaks typical of meteor showers. In contrast, meteoroids originating from asteroids tend to be stronger and more compact. These fragments can sometimes survive longer in the atmosphere and produce brighter meteors. But regardless of their origin, the majority of meteoroids are incredibly small. And yet their numbers are immense. Every day, Earth sweeps up tens of tons of cosmic dust as it moves through space. Most of this material arrives as microscopic particles that drift gently down through the atmosphere without producing visible meteors at all. But during meteor showers, slightly larger particles enter the atmosphere at higher speeds, creating the luminous streaks we see at night. So when we watch a meteor shower, we are witnessing countless tiny fragments of cosmic dust completing their long journeys through the solar system. Each one may have spent centuries orbiting the sun. Each one may have traveled millions of kilometers through space. And yet their final moment is brief, a flash of light lasting only seconds. A grain of dust meets the atmosphere of Earth. For a moment, the sky glows, and then the particle is gone. When we watch a meteor streak across the night sky, its motion seems almost instantaneous. One moment the stars are still and quiet, and the next moment a thin line of light appears, gliding across the darkness before vanishing completely. This sudden appearance and disappearance can make meteors feel mysterious, even magical. But behind that brief flash lies one of the most remarkable physical characteristics of meteor showers: their incredible speed. Meteoroids are among the fastest natural objects that regularly interact with Earth. By the time a meteoroid enters our atmosphere, it is often traveling at speeds that are difficult for the human mind to imagine. Typical meteor speeds range from about 11 kilometers per second to more than 70 kilometers per second. To understand just how fast this is, it helps to compare those speeds with something familiar. A commercial airplane travels at roughly 250 meters per second. A high-speed bullet might reach about 1 kilometer per second. But even the slowest meteors move more than 10 times faster than a bullet. At the upper end of the range, a meteoroid traveling at 70 kilometers per second is moving nearly 250,000 kilometers per hour. At that speed, the particle could travel from one side of Earth to the other in only a few minutes. Yet these incredible velocities are not unusual in space. Objects orbiting the sun must move quickly in order to remain in orbit. Earth itself travels around the sun at about 30 kilometers per second. Many meteoroids move along their own solar orbits at similar speeds. When Earth and a meteoroid meet, their relative motion determines how fast the particle strikes the atmosphere. Sometimes Earth catches up with slower-moving particles from behind. Other times meteoroids approach from the opposite direction, colliding with Earth head-on. In those cases, their speeds combine, producing some of the fastest meteor entries possible. The geometry of these encounters explains why different meteor showers have different typical speeds. Some showers are known for producing very fast meteors, while others appear slower and more graceful. For example, the Leonid meteor shower is famous for extremely fast meteors traveling around 71 kilometers per second. These meteors often produce long, bright streaks that flash across the sky in an instant. The Perseids, which occur each August, produce meteors traveling around 59 kilometers per second. These are also considered fast meteors and often leave beautiful glowing trails behind them. Other showers, such as the Geminids, produce slower meteors moving around 35 kilometers per second. While still incredibly fast by everyday standards, These slower meteors often appear smoother and more stately as they glide across the sky. The speed of a meteor has a strong influence on its appearance. Faster meteors tend to produce shorter, sharper flashes of light. Because they enter the atmosphere with such tremendous velocity, they burn up quickly and brightly. Slower meteors, on the other hand, may appear to travel a longer path across the sky before fading. But speed also affects the altitude at which meteors begin to glow. Very fast meteoroids start interacting with the atmosphere earlier, sometimes as high as 120 kilometers above Earth's surface. Their enormous speed means that even extremely thin air can generate intense heating. Slower meteoroids usually penetrate deeper into the atmosphere before becoming visible, because the thinner upper layers of air do not produce enough heating at their lower speeds. This difference means that meteor showers can have slightly different visual characteristics depending on the speed of their particles. Fast showers may produce quick flashes high in the sky. Slower showers may produce longer streaks that seem to glide more gently through the darkness. Another interesting effect of meteor speed is the brightness of the meteor itself. Because kinetic energy depends on the square of velocity, even small increases in speed dramatically increase the energy released during atmospheric entry. This means that very fast meteors can appear surprisingly bright even when the particles themselves are extremely small. A grain of dust traveling at 60 kilometers per second can produce a meteor visible across hundreds of kilometers of sky. The atmosphere transforms that tiny particle's enormous energy into light. Yet, despite their tremendous speeds, meteoroids rarely pose any danger to people on the ground. Most particles are so small that they vaporize completely long before reaching lower altitudes. Earth's atmosphere acts as an effective shield, absorbing the energy of incoming particles high above the surface. In fact, the atmosphere protects us so well that the majority of meteoroids never even come close to the ground. They arrive at incredible speed. They blaze briefly in the sky, and then they disappear entirely. But from our perspective on the ground, their speed becomes part of their beauty. The swift streak of light across the stars reminds us that the universe is not static or still. Even in the quiet darkness of night, the solar system is alive with motion. Planets orbit the sun, comets sweep through the inner solar system, and tiny fragments of cosmic debris race silently through space until they meet the atmosphere of our world. When they do, their incredible speed transforms them into one of the most peaceful spectacles in the sky. A sudden flash, a silent line of light, a reminder that even the smallest particles in the universe can move with astonishing power. When we think of meteors, many of us imagine a simple white streak of light gliding across the night sky. And indeed, many meteors do appear white or slightly yellow to the human eye. But if we observe carefully, especially during brighter meteor events, we may begin to notice that meteors can display subtle colors as they travel through the atmosphere. Some flash briefly with a hint of green. Others glow warm orange or golden yellow. Occasionally, a meteor may even show faint shades of red or blue along its path. These colors are not random. They reveal something fascinating about the physical nature of the meteoroid and the gases of Earth's atmosphere. When a meteoroid plunges into the atmosphere at high speed, the air around it becomes extremely hot, forming the glowing plasma we discussed earlier. Within that plasma, atoms from both the atmosphere and the meteoroid itself become energized. As those excited atoms return to lower energy states, They release light at very specific wavelengths. Each chemical element produces its own characteristic color. This process is similar to what happens in fireworks. When different metallic salts are heated in a firework explosion, they emit distinctive colors that create the familiar patterns we see in the sky. Meteors work in a somewhat similar way, although the process occurs naturally and at much higher speeds. One of the most common colors seen in meteors is yellow or orange. This color is often produced by sodium atoms. Sodium is abundant in many types of meteoroid material and can emit a warm golden light when heated. Even tiny amounts of sodium vapor can create a noticeable yellow glow along the meteor trail. Green is another color frequently observed in meteors, especially in brighter ones. Green light is often associated with magnesium, an element commonly found in rocky materials throughout the solar system. When magnesium atoms become excited in the intense heat of atmospheric entry, they can produce a striking green glow. Observers sometimes report bright meteors flashing with a vivid emerald color as they streak across the sky. Iron, another element commonly present in meteoroids, tends to produce yellowish or golden tones. Because iron is abundant in many rocky bodies, it often contributes to the overall brightness of meteor trails. Calcium can sometimes produce faint violet or purple hues, though these are often difficult to detect with the human eye. But the meteoroid itself is only part of the story. The atmosphere also plays an important role in determining meteor colors. The gases surrounding the meteoroid, primarily oxygen and nitrogen, become excited by the intense heat generated during atmospheric entry. Excited oxygen atoms can emit red or orange light, especially at higher altitudes where the atmosphere is thinner. Nitrogen molecules can produce bluish or purplish tones under certain conditions. Because the meteor trail contains a mixture of glowing atmospheric gases and vaporized meteoroid material, the resulting colors often blend together. The human eye may perceive this mixture as a soft white glow or a pale yellow streak. But sensitive cameras sometimes reveal subtle color variations that are difficult to see in real time. Long exposure photographs of meteor showers often show meteors with distinct green cores, orange edges, or faint blue halos. These color patterns reflect the complex physics occurring within the meteor's plasma trail. Speed also influences meteor color. Faster meteors generate more energetic collisions with atmospheric gases, producing higher temperatures and more intense excitation of atoms. This can enhance certain colors, especially those produced by atmospheric gases like nitrogen. Slower meteors may produce softer colors dominated by the elements within the meteoroid itself. Altitude also matters. High-altitude meteors often show reddish or orange tones because the thinner atmosphere allows oxygen emissions to dominate. As the meteoroid descends into denser layers of air, the colors may shift toward yellow or white as additional elements contribute to the glowing plasma. To an observer lying quietly beneath the stars, these subtle color variations add another layer of beauty to meteor showers. A faint meteor may glide silently overhead like a thin silver thread. A brighter one may flash briefly with green or gold before disappearing. Occasionally, a particularly brilliant meteor will blaze across the sky in multiple colors, leaving a glowing trail that slowly fades in the darkness. Each of these moments lasts only a few seconds. Yet within that brief flash, complex physical processes are unfolding. Atoms colliding, electrons shifting energy levels, and gases glowing in response to immense heat. It is a delicate display of physics written in light across the sky. A tiny fragment of cosmic dust enters the atmosphere. Its atoms mix with the air above our planet. For a moment, the elements of the universe shine together. And then, as quickly as it appeared, the colors fade back into the quiet darkness of night. As we move gently through the calendar of the night sky, certain meteor showers arrive with a kind of quiet reliability. Each year, as Earth continues its steady orbit around the Sun, it passes through familiar streams of cosmic debris left behind by ancient travelers of the solar system. One of the earliest major meteor showers of the year appears in the cold days of early January. This shower is known as the quadrantids. Unlike some meteor showers that remain active for many weeks, the quadrantids are known for something quite unusual: an extremely brief but powerful peak. For most of the days when the quadrantids are active, observers may see only a modest number of meteors. But for a short window, sometimes lasting only a few hours, the meteor rate can suddenly surge, producing dozens or even more than 100 meteors per hour under dark skies. Because this peak is so short, many observers miss the best part of the display unless the timing aligns perfectly with nighttime at their location. Yet, when conditions are favorable, the quadrantids can become one of the most impressive meteor showers of the entire year. The name quadrantids may sound unfamiliar compared to other meteor showers like the Perseids or Geminids. This is because the name refers to a constellation that no longer officially exists. Long ago, astronomers recognized a constellation called Quadrans Muralis, which means the mural quadrant. The name referred to an astronomical instrument used for measuring star positions. Over time, the constellation Quadrans Muralis fell out of use and was eventually removed from the official list of constellations established by the International Astronomical Union. However, the meteor shower discovered in that region of the sky had already been named, and so the quadrantids kept their historical name, even though the constellation itself has disappeared from modern star maps. Today, the radiant of the quadrantid meteor shower lies in the northern sky near the constellation Boötes, not far from the bright star Arcturus. For observers in the northern hemisphere, this radiant rises high in the sky during the early morning hours of January. Cold winter air often makes meteor watching a challenge during this time of year. Observers must bundle up carefully, sometimes lying beneath thick blankets while watching the sky. Yet those who brave the cold are often rewarded with a beautiful display. The meteors of the quadrantids are known for being relatively bright and swift. Many produce distinct streaks of light that briefly flash across the winter sky. The origin of the quadrantid meteor stream remained a mystery for many years. Most meteor showers are associated with comets, which shed dust as they approach the sun. But astronomers struggled to identify the parent comet responsible for the quadrantids. Eventually, scientists found a possible source in an unusual object known as 2003 EH1. This object appears somewhat asteroid-like rather than comet-like. It does not display the typical bright tail associated with active comets. However, its orbit matches the path of the quadrantid meteoroid stream remarkably well. Astronomers now believe that 2003 EH1 may actually be the remnant of an ancient comet that fragmented long ago. If this is true, the quadrantid meteor stream could represent debris released during a dramatic breakup event in the distant past. Over centuries, that debris spread along the orbit of the original object, forming the narrow dust stream that Earth encounters each January. The narrowness of this stream helps explain the brief but intense peak of the quadrantids. Unlike wider dust streams that stretch across large portions of Earth's orbit, the quadrantid stream is relatively compact. As a result, Earth passes through its densest region quickly, sometimes in just a few hours. During that short interval, the number of meteors can increase dramatically. Then, just as suddenly, the activity begins to decline again. For observers who happen to be watching during the peak, the sky can appear alive with motion. Streaks of light flash across the stars, one after another, each lasting only a moment before fading. And then, after the peak passes, the sky gradually returns to its usual quiet rhythm. Only a few occasional meteors appear, reminding us that the dust stream still lingers in space even as Earth continues on its path. Despite the challenges of winter weather and the short duration of its peak, the quadrantid meteor shower remains one of the most fascinating early events of the astronomical year. It arrives quietly, often overlooked amid the darkness of January nights. But for those who take the time to watch the sky, the quadrantids offer a peaceful reminder that even in the coldest part of the year, Earth is still moving through ancient rivers of cosmic dust. And for a few brief hours, the sky becomes filled with silent streaks of light. As the long arc of the year carries Earth forward along its orbit, the quiet cold of winter gradually softens into spring and summer. Nights grow warmer, the air becomes gentler, and for many observers the sky feels more inviting. It is during these warm summer nights that one of the most beloved meteor showers of all makes its appearance. This is the Perseid meteor shower. For many people around the world, the Perseids are the first meteor shower they ever experience. Their arrival each August coincides with comfortable nighttime temperatures in the northern hemisphere, making it easy to lie back beneath the stars and watch the sky for long stretches of time. Unlike some meteor showers that require patience to see even a few meteors, the Perseids are generous. Under dark skies, observers may see dozens of meteors each hour during the peak, sometimes even more. These meteors often glide gracefully across the sky, leaving bright trails that linger momentarily before dissolving into the darkness. Part of the Perseids' popularity comes from this combination of reliability and beauty. Every year, sometime between mid-July and late August, Earth passes through a stream of cosmic debris left behind by a comet known as Swift-Tuttle. This comet follows a long and elongated orbit around the Sun that takes approximately 133 years to complete. When Swift-Tuttle approaches the Sun, solar heat causes gas and dust to escape from the comet's surface. Tiny particles are released into space and gradually spread along the comet's orbital path. Over centuries, this debris forms a vast stream that continues circling the Sun even when the comet itself is far away in the outer solar system. Each August, Earth crosses this dusty pathway, and when it does, countless tiny fragments from Swift-Tuttle plunge into our atmosphere, producing the meteor shower we call the Perseids. The radiant of the Perseid meteor shower lies within the constellation Perseus. Perseus is a recognizable pattern of stars in the northern sky, though it is not among the brightest constellations. During August nights, it rises in the northeastern sky after sunset and climbs higher as the night progresses. As the radiant rises, meteor activity gradually increases. This is why Perseid meteors are often best observed after midnight, when the radiant has moved higher above the horizon. At that time, observers on the surface of Earth are facing more directly into the incoming stream of particles. But the Perseids offer more than just quantity. Their meteors are known for being particularly fast and often quite bright. Typical Perseid meteoroids enter the atmosphere at speeds of about 59 kilometers per second. This high velocity creates brilliant streaks of light that can stretch across large portions of the sky. Many Perseid meteors also produce persistent glowing trails. After the meteor itself disappears, a faint thread of light may remain visible for several seconds. These glowing trains slowly twist and fade as high-altitude winds move the ionized gas through the upper atmosphere. Watching these fading trails can feel almost hypnotic. The sky seems to breathe slowly, reshaping the delicate remnants of each meteor's passage. Another feature that makes the Perseids special is the frequent appearance of fireballs. Because the Perseid debris stream contains particles of varying sizes, occasional larger fragments enter the atmosphere and produce exceptionally bright meteors. These fireballs can flash dramatically across the sky, sometimes leaving trails that linger for many seconds. Observers often remember these bright events long after the meteor itself has vanished. But beyond their scientific explanation, the Perseids carry a long cultural history. For centuries, people across different regions of the world have watched this meteor shower and woven it into local traditions. In parts of Europe, the Perseids are sometimes called the Tears of St. Lawrence. The peak of the meteor shower occurs around August 10th, close to the feast day of St. Lawrence in the Christian calendar. According to tradition, the falling stars were said to represent the tears of the saint as they fell from heaven. Elsewhere, people simply associated the Perseids with summer nights spent outdoors beneath the stars. Families gather on blankets, astronomers set up telescopes nearby, and quiet watchers simply look upward, waiting for the next streak of light. Despite the centuries of observation, the Perseids remain as captivating as ever. Every year, the same dust stream waits patiently along Earth's orbital path. And every year, when our planet arrives at the right place in space, the sky responds. Tiny fragments of an ancient comet meet the atmosphere of Earth. They ignite briefly into light, and for a few warm nights each August, the heavens offer one of their most gentle and beautiful spectacles, a silent rain of summer meteors. As the year slowly moves toward its final months, the nights begin to grow longer again. The warmth of summer fades, and the crisp air of late autumn settles quietly across much of the world. With the return of longer nights comes another remarkable meteor shower, one that many astronomers consider the most reliable and impressive display of the year. This meteor shower is known as the Geminids. Unlike most meteor showers, which originate from comets, the Geminids have a very unusual source. Their parent body is not a comet at all, but an object known as 3200 Phaeton. Phaeton is classified as an asteroid, yet it behaves in ways that make it somewhat mysterious. It follows a highly elliptical orbit that brings it very close to the Sun, closer than the planet Mercury during parts of its journey. When Phaeton approaches the Sun, its surface experiences intense heating. Temperatures become so extreme that cracks may form in the rocky surface, allowing small fragments to break away and drift into space. Over time, these fragments have spread along Phaeton's orbit, forming a broad stream of debris. And every December, Earth passes through that stream. The result is the Geminid meteor shower. The radiant of the Geminids lies in the constellation Gemini, near the bright stars Castor and Pollux. As the night progresses, Gemini climbs higher into the sky, bringing the radiant with it. The peak of the Geminid meteor shower usually occurs around mid-December, often between the 13th and 14th. Under dark skies, the Geminids can produce more than 100 meteors per hour during their peak, sometimes even more under ideal conditions. Because of this, many astronomers consider the Geminids to be the most productive meteor shower of the entire year. One reason for this strong activity is the structure of the debris stream itself. The Geminid stream is relatively dense, meaning Earth encounters a large number of particles as it travels through the debris field. These particles vary in size, producing a wide range of meteor brightness. Some are faint, barely visible streaks. Others are bright, slow-moving meteors that glide gracefully across the winter sky. Compared with showers like the Perseids or Leonids, Geminid meteors move at a somewhat slower speed, roughly 35 kilometers per second. Although this is still extraordinarily fast, it is slower than many other meteor showers. This slower speed gives Geminid meteors a distinctive appearance. Instead of flashing quickly across the sky, many Geminid meteors appear to move more smoothly and steadily, leaving graceful streaks that last slightly longer than those produced by faster showers. Observers often describe Geminid meteors as bright and colorful. Because the particles originate from a rocky asteroid rather than a fragile comet, they tend to be denser and stronger. This allows them to survive slightly longer during atmospheric entry, producing brighter and sometimes more colorful meteors. Green and yellow hues are frequently observed in Geminid meteors, though subtle reds and blues may also appear. Another advantage of the Geminids is the timing of their peak. Unlike some meteor showers that reach maximum activity during the early morning hours, the Geminid radiant rises relatively early in the evening. This means that observers can begin seeing meteors shortly after sunset. As midnight approaches and the radiant climbs higher in the sky, the number of visible meteors usually increases. For observers willing to stay awake through the quiet hours before dawn, the display can become truly spectacular. Despite the cold temperatures of December in many parts of the world, the Geminids attract large numbers of skywatchers every year. Warm clothing, blankets, and hot drinks often accompany those who venture outside to watch the sky. And in the stillness of winter nights, the Geminids offer a peaceful spectacle. Streaks of light appear one after another across the dark sky. Some glide slowly across the stars. Others flash brightly before fading into the cold air above. Each meteor represents a tiny fragment of asteroid Phaeton completing its long journey through space. For centuries, those particles have orbited the sun quietly, waiting for the moment when Earth would pass through their path. When that moment arrives, the sky briefly fills with motion, a gentle cosmic snowfall of light. And as the meteor shower slowly fades in the days after its peak, Earth continues along its orbit once more, leaving behind the dust stream until the following year, when the Geminids return again to illuminate the quiet winter sky. If you have ever tried to watch a meteor shower, you may have noticed something curious. During the early evening hours, the sky can remain quiet for long periods of time. Only an occasional meteor appears, and sometimes none at all. But as the night grows deeper and midnight passes, the activity often increases. More streaks appear, the intervals between meteors grow shorter, and during the hours before dawn, the sky can suddenly feel alive with motion. This pattern is not a coincidence. It reflects the way Earth moves through space. To understand why the best time to watch a meteor shower is usually after midnight, we need to imagine Earth not as a stationary world, but as a rapidly moving traveler in orbit around the Sun. Our planet moves along its orbit at about 30 kilometers per second. At the same time, Earth rotates once every 24 hours, turning different parts of the planet toward the direction of its motion. This combination of orbital motion and rotation determines when observers on the surface are facing into the incoming stream of meteoroids. In the early evening hours, the part of Earth where you are standing is turned slightly away from the direction of Earth's orbital movement. In other words, your location is on the trailing side of the planet. Imagine riding in a car during a light snowfall. When you look out the back window, the snowflakes appear to drift gently past. But when you look out the front windshield, the snow seems to rush toward you. Meteor showers behave in a very similar way. When you are on the trailing side of Earth during the evening, the meteoroids approach the atmosphere from behind. Only a few particles catch up with Earth and enter the atmosphere above your location. But as the night progresses and Earth rotates, your position on the planet gradually moves toward the leading side, the side facing forward along Earth's orbit. After midnight, your part of Earth is essentially on the front of the moving planet. Now the situation changes dramatically. Instead of meteoroids slowly catching up from behind, Earth is actively sweeping into the stream of particles. It is like the windshield of the moving car meeting the snowfall head-on. As a result, many more meteoroids collide with the atmosphere above your location. This is why meteor activity increases after midnight. By the time the hours before dawn arrive, observers are facing directly into the direction Earth is traveling through space. During this time, meteor rates are often at their highest. Another advantage of the early morning hours is the position of the radiant in the sky. As Earth rotates, the radiant of a meteor shower rises higher above the horizon. When the radiant is low, many meteors occur below the horizon or enter the atmosphere at shallow angles that make them harder to see. But when the radiant climbs high into the sky, more meteoroids enter the atmosphere above the observer. This increases the number of visible meteors. For this reason, experienced observers often plan their meteor watching sessions during the hours between midnight and dawn. Of course, watching meteors does not require any special equipment. In fact, telescopes and binoculars are not particularly helpful for meteor showers. These instruments narrow the field of view, making it difficult to see meteors that may appear anywhere in the sky. The best approach is surprisingly simple. Find a comfortable place where the sky is wide and open. Lie back if possible, allowing your eyes to take in as much of the sky as possible. Then simply wait. Meteor watching is an activity that rewards patience and calm attention. There may be several minutes between meteors, especially during the quieter parts of the night. But eventually, a streak of light appears, then another, and perhaps another. Gradually, the rhythm of the meteor shower reveals itself. Some observers bring blankets or reclining chairs to make the experience more comfortable. Others travel far from cities to escape artificial lights that can hide the faintest meteors. Dark skies allow the eyes to adjust fully to the night. After about 20 minutes in darkness, the human eye becomes far more sensitive to faint light. During this time, the number of visible meteors can increase significantly. Even faint streaks that would otherwise go unnoticed become visible against the stars. And so meteor watching becomes less about equipment and more about quiet observation. You simply lie beneath the sky and allow the universe to reveal itself slowly. A streak appears, then darkness, then another faint flash across the stars. And as the hours pass and the Earth continues its journey through space, the meteor shower reaches its gentle peak, a silent display unfolding above a turning world. When people first hear about meteor showers, they sometimes imagine needing special equipment to see them clearly. Telescopes, binoculars, cameras, or perhaps complicated astronomical tools. But meteor showers are different from many other astronomical events. In fact, the best instrument for watching meteors is something we all already have: our eyes. Meteor showers are white sky events. Meteors can appear anywhere overhead, near the horizon, high above, or streaking from one side of the sky to the other. A telescope would only show a tiny patch of sky, causing most meteors to pass outside its narrow field of view. That is why astronomers and skywatchers almost always observe meteor showers with the naked eye. But although special equipment is not necessary, the environment around us plays a very important role in how many meteors we are able to see. The most important factor is darkness. Artificial light from cities creates a bright glow in the sky known as light pollution. This glow washes out faint stars and hides the dimmest meteors from view. In large cities, only the brightest meteors may be visible. But in rural areas far from city lights, the night sky becomes dramatically darker. Thousands of stars appear, and faint meteors that would otherwise be invisible become easy to notice. For this reason, experienced meteor watchers often travel away from urban areas to find darker skies. Open countryside, mountain ridges, deserts, and coastal areas can provide excellent viewing conditions. Even a short drive away from city lights can make a noticeable difference. The second important factor is having a wide, unobstructed view of the sky. Tall buildings, dense forests, and mountains can block portions of the sky where meteors might appear. A good observing location should have a clear horizon and a wide view overhead. Many observers choose open fields or quiet beaches where the sky stretches uninterrupted in all directions. Comfort also matters. Meteor showers often require long periods of quiet watching. Observers may lie back for hours waiting for meteors to appear. Because of this, many people bring reclining chairs, sleeping mats, or blankets to make the experience more comfortable. Warm clothing is also important, especially during meteor showers that occur in colder seasons. Even on mild nights, the body can lose heat quickly when sitting still for long periods under the open sky. Bringing warm layers, gloves, and perhaps a hot drink can make meteor watching far more enjoyable. Another helpful practice is allowing your eyes time to adjust to the darkness. When you first step outside at night, your eyes are still adapted to artificial light. It may take 15 to 20 minutes for them to fully adjust to the dim conditions of the night sky. During this time, the pupils widen and the eye becomes more sensitive to faint light. As this adaptation occurs, more stars become visible, and with them, more meteors. Avoiding bright lights during this time is important. Looking at a phone screen or bright flashlight can reset the eye's dark adaptation, making faint meteors harder to see. Some astronomers use red flashlights instead of white ones when reading star charts. Red light interferes less with night vision and allows the eyes to remain adapted to the darkness. Weather also plays a role. Clear skies are essential for meteor watching. Even thin clouds can block faint meteors, reducing the number of visible streaks. Observers often check weather forecasts carefully before planning a meteor shower observation. Sometimes the best skies appear unexpectedly. A calm night with perfectly clear air and countless stars shining quietly overhead. During such nights, meteor showers can feel almost magical. One final detail that surprises many people is that it is not necessary to look directly at the radiant of the meteor shower. In fact, looking slightly away from the radiant often provides a better view. Meteors that appear farther from the radiant tend to produce longer streaks across the sky. These longer paths make the meteors easier to notice and more visually striking. So the best strategy is simply to look toward a dark portion of the sky with as wide a view as possible. Then relax. Let your eyes wander slowly among the stars. And wait, meteor showers are not fast-paced events. They unfold gently, sometimes with long pauses between streaks of light. But that slow rhythm becomes part of their charm. You sit quietly beneath the sky. The world grows calm, and from time to time, a thin line of light crosses the darkness. A reminder that Earth is moving through a delicate stream of ancient cosmic dust. By now, as we quietly continue our exploration of meteor showers, 3 similar words may begin to appear again and again: meteoroid, meteor, and meteorite. At first glance, these words seem almost identical. They share the same root and are often used interchangeably in everyday conversation. But in astronomy, each word has a very specific meaning. Understanding the difference between them helps reveal the complete journey of these tiny fragments from space. Let us begin with the first stage: a meteoroid. A meteoroid is the object while it is still in space. It is simply a small piece of rock, metal, or dust drifting through the solar system. These fragments may originate from comets shedding debris, asteroids breaking apart after collisions, or even material blasted from the surfaces of planets and moons during ancient impacts. Most meteoroids are extremely small. Many are no larger than grains of sand. Some may be the size of pebbles, and only rarely do they reach sizes comparable to stones or larger rocks. While they remain in space, these particles move quietly along their own orbits around the sun. They are cold, dark, and invisible to the human eye. A meteoroid can travel for thousands or even millions of years without interacting with anything at all. It simply drifts through the vast emptiness of the solar system. But occasionally, one of these tiny travelers crosses paths with Earth. And when that happens, the second stage begins: the meteor. A meteor is the bright streak of light produced when a meteoroid enters Earth's atmosphere and heats the surrounding air. As we discussed earlier, the meteoroid collides with atmospheric molecules at extremely high speeds. The compressed air around the particle becomes superheated, forming a glowing trail of plasma. From the ground, we see this as a meteor, a shooting star briefly flashing across the night sky. The meteor itself is not the rock. It is the light created by the interaction between the meteoroid and the atmosphere. Most meteors last only a second or two before fading away. During that short time, the meteoroid often vaporizes completely, turning into gas and tiny fragments scattered high above Earth. But occasionally, something different happens. If the original meteoroid is large enough and strong enough, part of it may survive the intense heating of atmospheric entry. Instead of vaporizing entirely, a fragment continues falling toward the ground. When that fragment reaches Earth's surface, it enters the final stage of its journey. At that point, it becomes a meteorite. A meteorite is the piece of the original meteoroid that survives the fiery descent and lands on Earth. Meteorites can vary greatly in size. Some are small pebbles that quietly fall to the ground without much notice. Others can be much larger, sometimes weighing hundreds or even thousands of kilograms. These larger meteorites are rare, but they provide valuable clues about the formation of the solar system. Scientists study meteorites carefully because they are ancient materials that have remained largely unchanged since the early history of the solar system. Many meteorites formed more than 4.5 billion years ago, around the same time that planets were forming. By analyzing their composition, scientists can learn about the materials that existed in the early solar system. Meteorites are sometimes found by chance. A farmer may discover a strange rock in a field. A traveler might notice an unusual metallic object lying in the desert. Other meteorites are discovered through organized searches in places where they are easier to spot. One of the best locations for meteorite hunting is Antarctica. The dark rocks stand out clearly against the bright ice, and the slow movement of glaciers tends to concentrate meteorites in certain regions where they can be collected and studied. But despite these discoveries, meteorites reaching the ground are extremely rare compared to the number of meteoroids that enter Earth's atmosphere every day. Most particles are destroyed high above the surface. They become meteors, brief streaks of light, and then disappear completely. So the next time you see a shooting star flash across the sky, you are witnessing the middle stage of this journey. A meteoroid from space has entered the atmosphere. For a moment, it becomes a meteor. And in rare cases, if a fragment survives the descent, it may one day be found on the ground as a meteorite. 3 words describing 3 stages of a single cosmic traveler's story. From silent dust in space, to a streak of light in the sky, and sometimes, finally, to a stone resting quietly on Earth. As our quiet journey through the world of meteor showers slowly draws toward its final chapter, it is worth pausing for a moment to reflect on something remarkable. For as long as human beings have looked up at the night sky, meteors have captured our imagination. Long before telescopes existed, long before modern science gave us the language to describe meteoroids, plasma, or orbital mechanics, people noticed those sudden streaks of light. They saw stars fall, and they wondered why. Ancient observers across the world recorded these mysterious flashes in the sky. In China, some of the earliest written astronomical records include careful notes describing falling stars. Imperial astronomers observed the heavens night after night, documenting unusual celestial events that might carry significance for the emperor and the empire. These records stretch back more than 2,000 years, offering one of the longest continuous histories of sky observation in human culture. In ancient Greece, philosophers debated the nature of meteors. Some believed they were atmospheric phenomena, perhaps fiery vapors rising from the earth and igniting in the upper air. Aristotle, writing more than 2,000 years ago, proposed that meteors were part of the weather of the upper atmosphere rather than objects arriving from space. His explanation would remain influential for many centuries. Across other cultures, meteors were often interpreted as signs or messages. In parts of Europe during the Middle Ages, a sudden meteor might be seen as a warning from heaven. Some believed that shooting stars marked the birth or death of an important person. Others thought that a meteor represented a soul traveling between worlds. Many of these interpretations reflected humanity's deep emotional response to the night sky. When a meteor appears, it is sudden and unexpected. The sky, which usually seems calm and eternal, briefly becomes dynamic. Something changes. A streak of light moves across the stars. Then it disappears. Even today, people often react instinctively when they see a meteor. A common tradition around the world is to make a wish when a shooting star appears. The moment is so brief that the wish must be made quickly, a quiet hope whispered to the universe before the streak fades away. Although we now understand the scientific explanation behind meteors, the sense of wonder they inspire has not diminished. If anything, modern knowledge has made them even more fascinating. We know now that each meteor represents a tiny fragment of cosmic material that may have traveled through space for centuries or even thousands of years. A grain of dust released by a comet long ago. A small fragment from a distant asteroid. A particle drifting silently through the solar system. Eventually, its orbit intersects with that of Earth. And in that moment, its journey changes forever. The meteoroid plunges into the atmosphere. The air compresses, the plasma glows, and for a brief second, the sky lights up. From the ground, we see only the final moment of a journey that may have lasted longer than human civilization itself. The particle that creates a meteor tonight may have been traveling around the sun long before the pyramids were built, long before cities existed, long before recorded history, and yet its final moment appears above us, a quiet streak of light across the darkness. Meteor showers remind us that Earth is not isolated in space. Our planet moves constantly through a vast environment filled with dust, debris, and remnants of ancient celestial travelers. Invisible rivers of particles cross the solar system, and when Earth passes through them, the sky responds with delicate flashes of light. Each meteor is small. Each one lasts only seconds, but together they create a gentle cosmic display that connects our world to the broader universe. For those who lie quietly beneath the stars, watching the sky during a meteor shower can become a peaceful experience. There is no rush, no noise, only the quiet rhythm of waiting and watching. A streak appears, then darkness, then another faint flash somewhere across the sky. And as the night deepens and the stars continue their slow movement across the heavens, the meteors keep arriving one by one, tiny sparks from the vastness of space, brief moments of light in an otherwise silent sky, a reminder that even the smallest fragments of the universe can illuminate the darkness for just a moment before fading gently away. Now, as our exploration softly comes to rest, imagine once more that you are lying beneath the open sky. The night is calm. The air is cool and still. Above you, countless stars glow quietly across the vast darkness of space. Every now and then, a meteor glides silently overhead, a thin thread of light stretching briefly across the sky before fading back into the queue.